Reading week 5. For this week, the main physics idea was the review on torque and cross product, which was from physics 2211, and the magnetic field of single moving charge, currents, and currents flowing in straight wire and wire loop. So basically for torque, we already knew that torque is equal to the cross product of R and the force. And to find the cross product, we can make a 3x3 matrix and then use the determinant method to find the final vector that's in terms of I hat, j hat, and k hat. And we also learned that the right-hand rule can be used to see if the direction of torque was going into page or out of page. And then using this knowledge, we moved on to the topic of magnetic field. So for single moving charge, we learned that the B field, which is the magnetic field direction, is equal to the sine of Q times the cross product of V hat and R hat. And V is basically the direction of which the charge is moving, and R is the distance from the observation point. And then we also learned the Biot-Savart law, where it states the magnetic field, is equal to the magnetic constant times charge times the cross product of V and R hat over distance squared. Then using this basic Biot-Savart law for single charge particle, we're able to use that for currents and other current carrying configurations like a straight wire or a wire loop. I already knew how to calculate torque and cross product from last semester, and I was able to do right-hand rule to figure out the direction of torque. But what I did not already know was that using cross product can be applied onto finding the direction of magnetic field. And also another right-hand rule can be applied to see the B field direction for currents flowing in wires. Something interesting that I learned was that evaluating current carrying configuration is basically the same thing as last week's electric field of charge distributions calculation. So it's also in 3 steps. So first we just divide the current carrying configuration into pieces and use the B field equation to find the magnetic field for each piece. So a single piece can be calculated. And then lastly, we're going to use superposition to add all of the magnetic field of the pieces using integral, and we can simply find the sum of magnetic fields of the pieces. This relates to my major in terms of electrical engineering because it shows how magnetic fields form when currents flow through a wire. Lastly, it was confusing to me in terms of the difference of electric field and magnetic field. And so based on searching some images and articles on Google, I found out that electric field comes from charges. It's caused by charges and acts on charges around it, while magnetic field comes from moving charges and it acts on moving charges. And both of them exerts a force, but electric field exerts a force in terms of its electric field and the charge that's surrounding it. And for magnetic field, we know that force is applied onto moving charges, which is Q times V, and then we multiply that by B, which is the magnetic field. And on the right, you can see the different images that shows the electric field for point charge. And we don't have a magnetic field for point charge because it's not moving. And for infinite line of charge, you can see the image right over here, and on the rightmost, you can see the infinite plane of charge.